This is part C for our unit on confirmatory factor analysis. And up to this point, we've talked about how we build and specify confirmatory factor analysis models. We've talked about how we estimate parameters for our confirmatory factor analysis models. And now we're ready to talk about how we evaluate results. If you've done a study, you've collected data, and you set up a confirmatory factor analysis model, and you ran it, and you get all your output, how do you interpret that output? What do you look for? How do you draw conclusions about the results of your confirmatory factor analysis? How do you come to a conclusion about whether your instrument that you're evaluating has factor validity? As we go along here, we're going to see that there are three key things to look at when you evaluate a confirmatory factor analysis results. One is we want to look at the fit of the model. Another will be we want to look at the parameter estimates that we get when you estimate that model. And then a third thing, we'll want to look at alternate models. And one thing I want to point out as we go along here is that it will be important to look at all three of these things. One of the common mistakes I see people making when they do confirmatory factor analysis is they just focus on one thing and they ignore the others. For example, they might run a model and test the fit, and maybe the model has a really good fit. We get very good results regarding model fit. And then the person gets all excited and says, this is wonderful, my model has great fit, we have good factor validity, everything is wonderful, and I'm all excited about how good this model is. But it could be that the model has some serious problems in terms of maybe parameter estimates or in terms of looking at alternate models. And if a model has a problem in any one of these areas, we should not say it's a good model. We should not get excited and claim we have factor validity or say that the model is working well if it has a problem in any area. We want to satisfy criteria in all three of these areas before you say a model is working well. And I have this picture over here to illustrate the general idea. I think it might be a little bit like if you were trying to evaluate the utility of a car. And if you just looked at one thing, say you only looked at gas mileage, and you didn't look at, say, the power of the car or the comfort of the car or anything else, you just looked at gas mileage and nothing else, you might look at this car over here and say, well, this car has excellent gas mileage. It's just got this one guy pushing it, and so it doesn't use any gas at all, so it has wonderful gas mileage. Actually, I actually photoshopped that guy in there to give the point here, but so we have this car with excellent gas mileage. And if you looked at just gas mileage alone, and you didn't consider, well, how much power does the car have? How easy is it to drive? How comfortable is it? Or anything else, if you just looked at gas mileage, you would say, well, this is a wonderful car. But that would probably not be a very good conclusion to make because this car has a lot of serious problems in other areas. And it's the same thing when evaluating confirmatory factor analysis models. You don't want to just focus on, say, fit and nothing else. Just because it has good fit doesn't mean it's a good model. You want to look at all three of these areas before you draw conclusions about the overall utility of the model you're evaluating. So let's start by talking about fit. And we already talked about fit in our previous unit when we talked about using structural equation modeling to test regression models. And I'm going to talk about fit now again here. And if you recall from when we talked about it previously, we talked about using a chi-square significance test to test fit. And we also talked about something called fit indices that we can use to test fit. And we're going to use both of those things here as well. And I'm going to give you a little more detail at this point. So let's start with the chi-square significance test. So with this, we're going to get a chi-square value and use that value to do a significance test for our model. And specifically, we're going to test to see if there's a significant difference between S, that is our actual sample observed variance covariance matrix, and sigma, that is our reconstructed variance covariance matrix based on our confirmatory factor analysis model, based on which parameters we set to be free and fixed, and which items we said actually load on factors and which items don't load on factors. So given the way we specified our model, what do we get for our reconstructed variance covariance matrix, and how close does it come to our actual observed variance covariance matrix, and is there a significant difference between the two? And if there is a significant difference between the two, that means our model would essentially have poor fit. So in this case, what we really want is there for it not to be a significant difference, because if there's no significant difference between these two, that means our sigma is very close to our S. That means our reconstructed matrix is very close to the actual observed one, and so therefore that would be mean that our model has a good fit. So in this case, a significant chi-square means that the model has a bad fit, and a non-significant chi-square means that it has a good fit. Now, to be technically accurate, exactly what we're testing here, we're testing the null hypothesis. When we run a chi-square test, we're testing the null hypothesis that our model constraints are equal to the true population parameters. So if I constrain a pathway to be 0, if I say a particular item has a 0 loading on a factor, then I'm testing the null hypothesis that that constraint is actually what the true population parameter is. So when we're doing a chi-square test, we're testing the null hypothesis that the model constraints that we placed on our model are exactly what the true population parameters are. Now, to do this test, we need to get a chi-square value, and as it turns out, that's pretty easy to calculate. When we get our fit function, when we use our estimator to get a fit function, and this could be true, we could use the maximum likelihood fit function, or maybe we're using diagonally weighted least squares to get our fit function. Either way, we'll get a fit function, and we simply multiply it by our sample size minus 1, and that will produce the chi-square value. So that's how we get that. The extra chi-square value is simply equal to fit function times n minus 1, and that will give us a chi-square value, and then we could determine the probability of that chi-square value if this null hypothesis is true, and if it's if the probability is really small, we'd say the results are significant. That is, there's a significant difference between our two matrices, and we would reject the null hypothesis and claim that there's a difference between the two, which is not what we want to do. We want to say they're the same, so because they're significant, that would mean it's a poor model fit. So essentially, a significant means that our sample was large enough to detect an imperfect fit. Like all significance tests, this is based on your sample size. So here, you can see it right here. Our fit function is relative. We take a fit function times our sample size minus 1, which means we're going to get bigger and bigger values as our sample gets bigger. So if you have a really big sample, that means you have a lot of power to detect a difference between your two matrices. If you have a small sample, you don't have that much power. And that's one of the key limitations of using this chi-square test. It's a test that's driven largely by your sample size. If you have a large sample, and when you're doing confirmatory factor analysis, you really need to have a large sample. So you really need to have a large sample, and when you have a large sample, just about everything you touch is going to be significant. So, as I have down here at the very bottom here, this is actually not really a useful test for evaluating a hypothesized confirmatory factor analysis model. If you have a model that you think is your model you want to support, I would always report a chi-square test whenever I report results for a confirmatory factor analysis, but the chi-square results aren't going to be that informative here because hopefully you did a study with a large sample, and because you have a large sample, it's probably going to be significant. Now, there are many places where the significance can be useful, especially in places where you're trying to test an alternate model that you're hoping to reject. We'll do some things later on here where we'll test, say you have a hypothesis that your instrument has 2 factors, and we might want to test an alternate model that only has 1 factor. And so you'll compare your hypothesized model, which is a 2-factor model, with an alternate model that only has 1 factor and see if there's a difference. And we can do a chi-square test for a difference between those 2 models. And in that case, that will be a useful test. Also, as we saw in our previous unit, with regression, we could use this chi-square significance test to test a model where we constrain 2 beta weights to be equal. And if that model was significant, it meant we had a significant difference between those 2 beta weights, and that was a useful thing to test as well. So when we have a model that we're thinking as an alternate model, we might want to reject, whether it's an alternate unidimensional, say I'm doing a confirmatory factor analysis, and I have an alternate unidimensional model that I think isn't the real one, but I wanted to test it with the idea that I'm probably going to reject it. Or if I'm doing regression and I have two beta weights and I think they're different, but I'm going to test an alternate model where I constrain them to be equal and see if I can reject it, those are places where I would use a chi-square significance test. So if I'm testing an alternate model with the idea that I'm hoping to reject it, the chi-square significance test can be useful. But in situations where I have a hypothesized model and I'm wanting to support it, the chi-square isn't very useful because in this case I simply have too much power. If I have a large sample, just about everything I look at is going to be significant, and it's really not going to tell me a whole lot. So even though the chi-square significance test is not all that useful to us if we're wanting to evaluate the fit of a confirmatory factor analysis model, or specifically if we're evaluating the fit of a hypothesized model that we want to support, even though it's not all that useful for that, the chi-square significance test is something that is almost always reported whenever you do any kind of structural equation modeling. So if you do a confirmatory factor analysis, it's still common practice to report the chi-square significance test. And when you do that, you also want to keep track of whether you're treating your items as continuous or ordinal. We talked about that previously and noted that items, if they only have a few levels to them, they should be treated as discrete or ordinal. And if they have many, many levels, then they can function more like continuous items. So for example, if I have items on a questionnaire that are rated on a 5-point scale, I should probably treat those items as being ordinal or discrete. And in our previous video, we looked at how we could use the diagonally weighted least squares as our estimator when we have ordinal items or discrete items, and we can use maximum likelihood when we have items that have enough levels that we could treat them as if they're continuous. So if our items are ordinal, for example, if you have items on a questionnaire and they only have maybe 5 or 7 response options for each items, then we should treat them as ordinal or discrete. And when we have ordinal or discrete items, it's common to make an adjustment to the chi-square value. So once you calculate the chi-square, then the typical thing is to adjust it. Now this is, I have a note, there's actually probably a need for some more research to clarify exactly what happens. I've seen a few different ideas about ways to adjust it and what happens if you use different cutoff values for different fit statistics that these can get plugged into. And so we're treading into an area where there's somewhat of an unknown factor here about exactly how well these things work. But I have here some different ways, even though it's a little bit unknown, but here's some common ways that the chi-square is adjusted. So it's not just one way to adjust it, but people have different ideas about how to adjust it. If you're using R, the computer package R, with the Lavon package within R, it will give you something called a robust result. It'll give you values. It'll give you a chi-square value, an output that's labeled as robust. And where Lavon calls robust, that just means it's using that adjusted chi-square value, because you have, if you've told Lavon that you have ordinal or discrete items, then it will give you output that includes a section where it says, here's the robust results. And that simply means here's the results where we're doing this adjustment to our chi-square value because you have ordinal items. When I talked about diagonally weighted least squares, I gave you some different types. We talked about how diagonally weighted least squares is the same thing as robust weighted least squares, which is the same thing as this thing called weighted least squares mean and variance adjusted. And actually this term right here, noting that the phrase mean and variance adjusted is referring to the fact, or actually in this case it's a particular way in which this chi-square value is getting adjusted. So that's just that mean and variance adjusted part here. This MV, or mean and variance adjusted, that's just referring to how they're adjusting that chi-square value after they get it, given the fact that the items are ordinal. And this is something you would only do if you have ordinal items. And so that mean and variance adjusted phrase is just referring to the fact that they're adjusting the chi-square because you have ordinal items. And a third way, or another way to think, I have a Sertona-Bentler this is a bit older, but it used to be a fairly common type of chi-square adjustment. These two are slightly different approaches. They're not exactly the same thing. And the key thing to note is simply that when you have ordinal or discrete items, it is common practice to give an adjusted chi-square. There's a few different ways of doing it. This mean and variance adjusted approach, or the Sertona-Bentler approach, there's a few different ways, but it's common to adjust your chi-square even though at this point I think it's a little bit unknown exactly what those adjustments do. I think we need a little more research to clarify exactly how well they work, even though it's common practice to do them. I haven't seen any papers, at least recently, that have clarified exactly how well these adjustments are working. So if the chi-square significance test isn't very helpful for evaluating fit, what is helpful? And the way to evaluate the fit, the primary way to evaluate fit of a confirmatory factor analysis model is to use a fit index. And we talked briefly about fit indices before in our unit when we introduced structural equation modeling for evaluating regression models. So let's take a closer look at these fit indices. So a fit index is going to give us a measure of extent of fit. It won't be like a significance test. Like a significance test is dichotomous. Either results are significant or not. In this case, a fit index is going to be measure the extent of fit. It's going to give us a value that will range from high to low, and we can use some kind of arbitrary cutoffs if we want to, but these are all going to be index values that will range from high to low. They'll give us a measure of to what extent does our model fit. And again, when I say fit, I'm talking about the relationship between that reconstructed variance covariance matrix and the actual observed variance covariance matrix. How close does a reconstructed variance covariance matrix come to the actual data that we have in our sample? And that's what when we're talking about fit, we're talking about the relationship between those two matrices. And so there's a few different fit indices we can use to measure the extent or magnitude of fit. How well does our model fit? For the most part, these fit indices, unlike the chi-square, which is really a measure of how big your sample is, these fit indices are not influenced by sample size. I have here a note with some exceptions. There's actually some of the fit indices are slightly influenced by sample size, but for the most part, they're really not influenced. And if they are influenced, they're not influenced that much by sample size. And like I mentioned, the chi-square significance test was primarily not useful when you have a hypothesized model you want to accept or support, and these fit indices are useful when you have a hypothesized model you hope to accept. So when you have a factor structure and you say, this is the factor structure that I think represents a scale. If I have an instrument and I think my instrument has two factors on it, and I test my two-factor model, if that's what I'm testing, if that's my hypothesized model, and I'm hoping to find support for that model, then the fit index, one of these fit indices that I'm talking about, these are the things to use to see, to look for support for a hypothesized model that you hope to accept. And we're going to talk about three different fit indices. There's many. There's actually, we can actually go on. There's like dozens of fit indices out there. People have all kinds of formulas for different ways for calculating fit. But I want to talk about three fit indices that are probably the most popular ones, and I think the most useful ones to use in evaluating a confirmatory factor analysis model, or actually in evaluating most structural equation models. So I want to talk about a comparative fit index, something called a root mean square error of approximation, and something called a standardized root mean residual. And like I said, there's many other types of fit indices, but I want to focus on just these three. So let's take a look at these three fit indices and see what they are and how they work. So first, let's talk about the comparative fit index, or often abbreviated CFI for comparative fit index. So what is the comparative fit index? So what we're going to do, say I have my hypothesized model, here's my confirmatory factor analysis model over here on the left. This is the one we've been looking at in our previous examples, where I've got two factors, factor 1 and factor 2, and each factor has three indicators. Say I have a questionnaire with 6 items, and 3 of the items are measuring factor 1, and the other 3 items are measuring factor 2, and I'm allowing my 2 factors to correlate. So there's my basic confirmatory factor analysis model that I'm testing. This is the one I'm building that I want to support. And then I'm going to contrast my hypothesized model with this alternate model I'm going to call the independence model. And for the independence model, I'm going to make a model, and I'm going to see how bad I can make it. I want to make the worst possible model that I can imagine. In other words, I want to make the model that has the worst possible fit. How bad can I make the fit? And if I want to make the fit really bad, the thing to do is simply constrain everything. Recall that if you have a saturated model with no constraints, it will fit perfectly. And the more you put constraints on your model, the worse it will fit. And so if I just constrain everything, make every possible constraint I can make, then that will produce the worst possible fitting model there is. So here I have a model, and there's no lines or arrows, there's no path or anything. I just said, here are 6 variables, and essentially this is a model that says there's zero correlation, zero relationship, no paths, nothing going on, just 6 completely orthogonal, unrelated variables. And so this is essentially a model that I've put everything that's possible to constrain, I have constrained. I just said there's 6 variables, and there's no relationship whatsoever between them. And this model will produce the worst possible fit there is. And what I want to do is I want to compare how well does my model fit, my hypothesized model, how well does it compare to this alternate independence model that's as bad as it possibly can be. So compared to how bad things possibly can be, how good is my model? That's the question we're going to address here. And to do that, I'm simply going to calculate the chi-square value for my model, and then calculate the chi-square value for this independence model, and compare these two chi-squares. Note that if I was doing an analysis with orthogonal or discrete items, I might use my adjusted chi-square for this test. But I get my chi-square for my model, and the chi-square from this independence model where I've put all the possible constraints on it, and I'm going to define my independence model, whatever chi-square value I get. I'm going to say this represents 100% badness. So here's my little block here. So it's this tall. Say this is how bad, this is the size of the badness. If I were to make something as bad as it possibly can be, this block right here, whatever my chi-square value, that's 100% of the badness possibility. So compared to that, how big is this? So here I have, so this chi-square should be smaller. What I'm trying to illustrate here is say this chi-square for my model should be a much smaller value. So I have a small box over here, and say the chi-square value for my independence model should be really, really big value. Should get a really big value because it's a very bad model. So here's how big my independence model badness is. How big is my chi-square value from my model? How much does that compare to this 100% bad model? So we're going to compare these two chi-square values. And here is the formula for a comparative fit index right here. We're going to essentially take 1 minus the fit of my hypothesized model divided by the fit of this independence worst possible model. And the important thing to know is that when we plug this formula in to get a comparative fit index, what it's going to do, it's going to tell us how much does our hypothesized model improve upon the worst possible model. So this is the key thing to know. When we do a comparative fit index, it tells us how much our hypothesized model improves upon the worst possible model in terms of a percentage. So is our hypothesized model 50% better, 90% better, 95% better? How much better is it? And how much better does it need to be before we say this has a good fit? That's somewhat of an arbitrary question. When the comparative fit index was first proposed and people were first using it, they used to say that 0.9, that is, if your hypothesized model is 90% better than the worst possible model, that a 0.9 would be a good fit. Since then, other papers have come out and other simulation studies have suggested that 0.9 is probably a bit too liberal. We should probably set it more around 0.95. So I'm going to suggest to you, just to give you an arbitrary cutoff, we're going to say that if you do a comparative fit index and you get a value of 0.95 or higher, you can call that a good fit. And if it's less than 0.95, then we've got fit problems. So to be able to call a model, say it has a good fit using the comparative fit index, what we want to find is a comparative fit index of 0.95 or higher, meaning that your model is essentially 95% better than the worst possible model. So next, let's look at something called the root mean square error of approximation. So where the comparative fit index compared our hypothesized model with the worst possible model that there could be, now we're going to take our hypothesized model and compare it to the best possible model that could be. That would be a saturated model that will have perfect fit. So I'm going to take my model that we specified here, and we can see how well our model fits, like what type of chi-square we get for this model, and then we're going to compare that with a completely saturated model that will have 0 degrees of freedom. And so it will have, in this case, our chi-square is going to be 0, because if we have perfect fit, then your chi-square value will be 0. Here I have a picture of a saturated model. If you have 6 variables or 6 items, there's many different ways that you can make a model saturated. One way that you could get a saturated model is you just say every variable correlates with every other variable. So I've just drawn all the possible correlations between all my items here, just to say that everything correlates with everything. And so if I allow all the possible correlations, at this point the model has become saturated. And if we were to test this model, it would have a perfect fit, and the chi-square value would be 0 because it has a perfect fit. So let's compare, let's look at a way that we can compare our hypothesized model. How can we evaluate the fit of our hypothesized model and compare it to this completely saturated model that will have a perfect fit? And here is our formula for the root mean squared error of approximation. Essentially what we have in this formula, here in this numerator part right here, that's essentially we can call that a degrees of freedom corrected fit function. Recall that the chi-square value, we got that by taking our fit function times our sample size. And so in this formula over here, we're taking our chi-square divided by our sample size. Here it's n-1, here it's n, but very similar here. So chi-square, we took fit function times sample size. Here we're getting chi-square divided by sample size. So we're going from our chi-square back down to the fit function, but we've got this subtracting degrees of freedom from it, so we can call that, it's a degrees of freedom corrected fit function. And this partly is a little thing that's taking into account the fact that your degrees of freedom have to do with how many constraints you're placing on the model, and when you're putting a lot of constraints on your model, it makes it more and more difficult for it to fit. And in some ways that can be kind of a punishing thing, that if you want to make models that fit really well, just don't put many constraints on it. So it's kind of trying to offset that punishment a bit, so that you're not quite punished so much by having lots of constraints on your model, if that's the type of model you're testing. So we've got this degrees of freedom corrected fit function value in our numerator, and then we divide it by our degrees of freedom, and at this point our equation is simply giving us the average or the mean squared error for each constraint. So on average, if you have 5 constraints, on average, what is the squared error for that constraint? How much problem is that constraint causing? So we're getting a squared error for each constraint and taking the average, essentially, is what we're getting here. So this is going to give us the average or the mean squared error for each constraint. And then we're going to say, well, we don't want to be looking at this in these squared values, because the chi-squared, initially that's a formula that's giving us, we're measuring the badness of the fit, we're measuring it in squared units. And so we want to unsquare it and turn it back into unsquared units. So we're going to simply take the square root of this mean squared error. So we take the square root, and that's what we call it. It's the root mean squared error of approximation. And that is another way of testing fit. And the root mean square error of approximation is something that you want this value to be as low as possible. A low number means a good fit. So it's the opposite of the comparative fit index. The comparative fit index was something where a higher value meant a good fit. With the root mean square error of approximation, a lower value means a good fit. So that raises the question, how low does it have to be before you say your model has a good fit? And again, that's an arbitrary question, or the answer to that is an arbitrary answer, but we can give some arbitrary cutoffs, some rules of thumb to follow to help make that judgment. So with the root mean square error of approximation, a score of 0 would mean you have a perfect fit. If you, for example, if you had a saturated model, everything, your chi-square would be perfect, and you would have a perfect fit. So your root mean square error of approximation would be 0. So 0 means perfect fit. And as the numbers get bigger and bigger, it means you're getting a worse and worse fit. One rule of thumb to say is that if your root mean square error of approximation is 0.06 or less, you can call it a good fit. In fact, I would say if your root mean square error of approximation is 0.6 or less, you can definitely call that a good fit. That's a really good root mean square error of approximation value. Especially if you're doing confirmatory factor analysis models, a lot of times it is really hard to get it really that low. And I'd say for a lot of situations, we could probably say 0.8 is still going to be a reasonable fit for most of the stuff we do, especially with confirmatory factor analysis types of models. They tend to be a little bit higher for this particular measure of fit, I've noticed. So I would say that if you get 0.8 or smaller, you can still say that's a reasonable fit for this root mean square error of approximation. On one hand, the root mean square error of approximation is a very widely used fit index. On the other hand, it does have a couple drawbacks, which I've noted down here at the bottom, is that it tends to over-reject models. It tends to give you a value that's too high. It tends to be a little bit overly conservative and reject models more often than it's needed, especially when your sample size is small. For example, if it's less than 250 cases or people in your sample, this one's probably going to give you a little bit of an inflated value, which makes it more likely to look like a bad fit. Also, if your degrees of freedom are small, so for example, if you have fewer than 10 degrees of freedom, so this works well if you have a big model with lots of constraints, it can work well, but if you have a model that doesn't have that, for example, we were looking at that confirmatory factor analysis model that just had 2 factors and 6 items, that didn't have very many degrees of freedom, so that could be a little bit problematic as well. So when you have models that aren't that big and you don't have that many degrees of freedom, and if you have small samples, this value tends to be a little bit high and it tends to over-reject models. So it's not always the best one to use, although it is actually one of the most widely used ones in spite of that. And the third fit index I want to talk about is the standardized root mean residual. And before I talk about that, first let me talk about simply the root mean residual, and then I'll talk about the standardized root mean residual. And we've actually already talked about root mean residuals before. We talked about it, for example, when we talked in our previous unit on exploratory factor analysis. And we've talked about how if we have our S matrix, our variance covariance matrix from our sample, and we have our sigma matrix, our reconstructed variance covariance matrix based on our model. So here I have my 2 matrices. Here's, say, my sample matrix, and here's my reconstructed matrix. We can simply take, for each cell, take the value here minus the one there. Take the one here minus the one there. Take the value from our sample matrix minus the value from our reconstructed matrix to get S minus sigma, and then we square that value and sum that up to get a sum of squared residuals for comparing these 2 matrices. And as you think about it, that sum of squared residuals is going to be a big value if these 2 matrices are different from each other, and it's going to be a small value if these 2 matrices are similar to each other. So this is a value that's going to increase as your fit gets worse and worse. So once we have our sum of squared residuals, we can divide that by the number of elements in the variance covariance matrix, and that will give you the average squared residual, or the mean squared residual. And then if you want to evaluate that value in non-squared units, we can unsquare it, or we can take the square root. And if we take the square root of our mean squared residual, that will give us the thing we call the root mean residual. So the root mean residual is simply the square root of the mean square residual, where the mean square residual is the sum of the squared residuals divided by the number of elements. Now, this does give us a value that will get bigger and bigger as the fit gets worse and worse, and it will get smaller and smaller as the fit gets better and better. But it's difficult to interpret in terms of exactly what value represents a good fit or a bad fit. It's actually almost impossible to interpret the root mean residual by itself. And so we want to do something to make this easy to interpret. And we're going to do that by just assuming, or we turn all of our variables into z-scores. That will give us a value we can interpret. And we're going to call that the standardized root mean residual. So the standardized root mean residual is simply the root mean residual that we would get if everything is turned to z-scores, which actually we've been assuming that all along. So we're just going to assume that again here. If we turn everything to z-scores prior to analysis and calculate the root mean residual based on z-scores, that gives us the standardized root mean residual. And this is something we can interpret, and I can give you some guidelines about what might represent a good fit or a bad fit. And the one guideline I'm going to give you here is we're going to say that if your standardized root mean residual is 0.08 or less, that indicates a good fit. And if it's greater than 0.08, we're going to call that a poor fit. So this is just like the root mean square error of approximation, in that a small value is good, high values are bad. It's not like the comparative fit index, which we wanted a high value there. So for the standardized root mean residual, we want the value to be as small as it possibly can be. That indicates a good fit. And the rule of thumb I'll give you here is that we're going to say a value of 0.08 or less, we'll call that a good fit. And as we've been going along here, I've been giving you some different rules of thumb for different fit indices about what constitutes a good fit or a bad fit, and suggesting some possible cutoffs that you could use to determine whether a model has a good or bad fit. And one thing you might have wondered, or maybe not, but you might have wondered, who comes up with this stuff? How do they decide what we should call a good fit or a bad fit? And one of the ways that researchers have gone about evaluating fit indices to decide what we should use as cutoffs for good and bad fit is to run Monte Carlo simulations. This is a type of study where you just do it all on a computer, and you take a computer and you build a population. So for example, I might say, I'm going to say there's this population, and we have, say, an instrument that has say these different items on it. And I'm going to say, maybe here's my factor, and I say that these items load on this factor, and maybe I have another factor, and these items load, maybe I have a two-factor model here. And I've got the different items. That's a very quick, but imagine that's a two-factor structure, very abstract looking, a very abstract two-factor model. And then I'll say, well, maybe I have another model here. Maybe I have a different one. Maybe I have a third factor here, and I've got items loading on my third factor. Or maybe I say, well, this item actually loads over here. This one loads over here. So I'm going to try some different models, maybe a two-factor model or a three-factor model, and I'm going to build a population saying this is what the true factor structure is in this population. So I've got a set of items and a certain factor structure, and I'm going to build in my computer, I'm going to build a population that says this factor structure with these items and these factors, this is what the true population factor structure is. And then once I've used my computer to build this population, I'm going to take samples from that population in my computer and say, get a sample of 200 people or 200 cases from that hypothetical population that I've created on my computer, and get a sample of say 200 cases, and then run a confirmatory factor analysis on that hypothetical sample that I just collected, and get the results of my confirmatory factor analysis, and we'll get results on our fit indices. We'll get a confirmatory factor analysis, and we'll get our comparative fit index and our root mean square error of approximation and our standardized root mean residual. We'll get all of our fit indices, and then we'll see what they are. And we can look, because in this case we know what the true population is, because we made the population and we determined exactly what the factor structure was and made a population based on that factor structure. So we know what the true population parameters are. So we can see how did our fit indices perform given that we know what the true population parameters are. And usually when they do this type of research, they wouldn't just take one sample, they'd take many samples. So they have the population, they take a sample from that population and do a confirmatory factor analysis and get all the fit indices. And then they take another sample, do a confirmatory factor analysis, get all the fit indices, and they do that over and over and over again. and then they see how well the different fit indices perform under different circumstances. One of the most famous papers that looked at that was a paper by authors Hugh and Bentler. And this is a very widely cited paper. People that don't like arbitrary cutoffs hate this paper, hate they did that. And actually, Hugh and Bentler, in their paper, they said, here's a bunch of information you can use for deciding about cutoffs, but we're not trying to make any hard and fast rules. There's always a degree of subjectiveness in trying to make cutoffs. There's no hard, fast rules that we can perform, but they gave a lot of data from a whole bunch of simulations they ran to help provide guidelines about what we might use as cutoffs. And so what I have on this slide is basically a summary that in the Hugh and Bentler paper, they looked at many different possibilities and suggested many different scenarios. They said, well, here's one way we could make cutoffs, and here's another way, and here's just one my own summary of what they were looking at and trying to boil it down to something more concrete we could use, which people that don't like cutoffs probably hate the fact that I'm trying to boil it down to something simple like this. But in terms of having something practical for doing analysis and written results, this is a useful thing to do. So here are my suggested, these are some, there's many other possible things we could suggest here, but here's some of the cutoff values from the Hugh and Bentler paper that worked well based on their Monte Carlo simulations. And I have two different options here. The first one is if you're just going to use one fit index by itself. So I have these stand-alone values. This would be if you're just going to look at one fit index and nothing else. So, and these are actually the values I already gave you. So for the comparative fit index, something that's equal to or greater than 0.95, we'll call that a good fit. For the root mean square error of approximation, less than or equal to 0.06, although there's also some other stuff where we might be able to take 0.08 for that one. For the standardized root mean residual, we want that one to be equal to or less than 0.08 there. But actually a better approach, and this is the one that I'm going to suggest that you use in this class, and in the future, this is the one that I pretty much almost always use myself, is to do what would be called a two-index strategy. And in their paper, again, they have many different two-index strategies that you could possibly use. The one that I like is going to use the comparative fit index and the standardized root mean residual together. So in this case, we have two criteria, and it needs to meet both criteria before we call it a good fit. And so this is, for this particular two-index strategy, I want my comparative fit index to be greater than or equal to 0.95, and my standardized root mean residual to be equal to or less than 0.09. Note that this is the same as that. This one's actually a little bit more lenient. And that's because by using these two together, this one doesn't need to be quite so stringent. So with this two-index strategy, you need to pass both these criteria. So if I had a model and say the comparative fit index was 0.97, well, that's good. But the standardized root mean residual was 0.11. Well, that's bad. So if it doesn't fit that one, but it does fit that one, I'd say it's got a bad fit. It needs to fit both. It needs to pass both criteria before you call it a good fit. If you're following this two-index strategy, it's a strategy where you use these two fit indices and say it has to pass both before you call it a good fit. If there's either one of these has a poor fit, or both, but just even if you had just one has a poor fit, then you call it a poor fit. And that's partly why we were able to relax this just a little bit, was because I'm using this two-index strategy, because it needs to be, the standardized root mean residual needs to be 0.09 or less, and also the comparative fit index needs to be greater than 0.95 together. And that is the strategy I would suggest that you use in general for this class and in your own research. That is the one that my own opinion is that's probably the best way to go. So up to this point, we've been talking about ways to evaluate the fit of the model. And this slide is once again reminding us that there's more to evaluating a model than just looking at fit. We don't want to look at just fit and stop, but we also need to look at parameter estimates and alternate models. So if I do a study and I do a confirmatory factor analysis and say I use that two-index strategy to evaluate fit, and maybe I get a wonderful comparative fit index value. Maybe my comparative fit index value is 0.97. That's pretty good. And maybe my standardized root mean residual is, maybe it's only 0.04. That would be a pretty good value, and that would pass that 2-index strategy. And so I could say I have a great fit. But just because I have a great fit doesn't mean my model is working well. It doesn't mean I have factor validity, because I also need to consider parameter estimates and alternate models. So let's take a look at some of these other things. And also, as we go along here, I want to also go back and talk about fit and clarify exactly what do we learn when we look at fit. What does fit tell us, and how is that different from what we learn when we look at the parameter estimates and when we look at alternate models? So we want to look at these three things and also clarify exactly what do we learn when we look at each of these things. So first, let's consider fit. What do we learn when we look at the fit of a model? When we get a fit index and look at the results from a fit index, what exactly does that tell us? So fit is going to give us information on the constraints that we placed on a model. So again, when we're doing structural equation modeling and we get our reconstructed variance covariance matrix and our actual observed sample variance covariance matrix, and we're looking at the difference between those two matrices, and when there's a big difference between our sigma and our S, between our reconstructed matrix and our sample matrix, when there's a big difference between those two matrices, we have poor fit. And when those two matrices are similar to each other, we have a good fit. And the thing that makes those matrices different is when we put constraints on our model. If I had a model with no constraints, it would fit perfectly. And the more I put constraints on the model, the more I'm giving it more and more opportunities to have a poor fit. So it's more challenging to get fit. The more I put constraints on my model, the more of a challenge it is to get that model to fit. So when I look at a fit index, it's giving its information about the reasonableness of the constraints. How much damage do I do to my model when I add this constraint? Is everything really still okay? And it really doesn't make that much difference. So I'm wanting to have a model that I can put constraints on and still have a good fit in spite of the constraints that I place in that model. So the fit is giving me information about my constraints. It's giving me information about the reasonableness of the constraints. So to interpret fit, to understand what fit is telling us, we need to think about what are the constraints we placed on our model. So when we do a confirmatory factor analysis, what are the types of constraints we placed on that model? And that will give us information about what the fit means. And here I have some examples. So if we consider the constraints we placed on the model, that we can then decide what are the types of problems that might be indicated by a poor fit. So if we get a poor fit, what does that mean? So here are some possible problems. Here are some possible things that could cause a poor fit. These are things to look at if you get a poor fit. These are essentially the possible reasons why a model might have a poor fit. So one possibility is that you have items that need to load on multiple factors, or you have items that you specified loading on the wrong factors. So recall that when you create this confirmatory factor analysis model, you have a theory that each item, ideally, you should have each item should load on one and only one factor. So if you have maybe factor 1, maybe there's 8 items on a questionnaire that are all indicators of factor 1. Those 8 items should be indicators of factor 1 and not indicators of factor 2, and they should all have loadings on factor 1. But what if some of those items load on both factor 1 and factor 2, or they want to load? That is, some of those items are equally good indicators of factor 1, and they're also good indicators of factor 2. So in that case, you'd have items that are not specific. Your theory is that those items should all be specific to factor 1. So if, for example, you had a scale that was supposed to be measuring anxiety and depression, maybe factor 1 was how much people felt depressed, and factor 2 was supposed to be how much they felt anxious. And maybe you had an item on your depression scale that was something like, sometimes I feel really upset. But maybe when people look at upset, they mean both depressed and anxious, and they really can't distinguish between the two. So that item would load on both the depression factor and the anxiety factor. And if your model says it only loads on the depression factor, that would produce a poor fit, because that item, you might say it wants to load on both factors, but your model specifies it loading on only one factor. And if the item actually is an indicator of 2 factors and you specify it as only an indicator of only one factor, that will produce a poor fit. So items that need to load on multiple factors would produce a poor fit. And you don't, when you're doing confirmatory factor analysis and when you're developing scales, we don't want items that are just general items that are not specific to a single factor because they're vague and they don't really give us precise information. We want items that load on only one factor. So if you have an item that wants to load on multiple factors, that will produce a poor fit, and that would be a problem. And maybe that's an item that we should get rid of or modify or adjust. Or even worse, maybe I have an item that's loading on the wrong factor. Maybe I have an item that I thought was supposed to be measuring depression, but in truth, it's actually measuring anxiety. And so my theory is, and my scale has it set up, so it's supposed to be an indicator of the depression scale. But if in truth it's really a measure of anxiety, then I have my model with that item loading on the wrong factor. And that would also produce a poor fit. So if I have items that want to load on multiple factors, or items that are specified to load on the wrong factors, that would produce a poor fit. So that's one of the types of things that a fit index would tell us. It would tell us if we had a poor fit, that's one of the possible reasons that could cause a poor fit. Another thing that could cause a poor fit is that if our error variances need to correlate. Recall that when you create a confirmatory factor analysis model, we set all the correlations between our error variances to be zero. That is, our hypothesis should be that after the factors explain all the variance they can explain, there's no residual variance that's not explained by the factors that's left over that correlates with stuff. It's just all measurement error. That the factors explain all the important stuff and all the residuals are simply measurement error, and so therefore we shouldn't have correlations between the residuals of our items. And but if actually there was a correlation between the residuals, if we actually had some items that after the factor was extracted out of them, they still shared something together, they still had some kind of association with each other, even after accounting for their shared variance with a factor, if their residual variance was correlated in truth, then when we do our model and we specify those variances to be zero, when we specify those correlations between their error variances to be zero, that will create a poor fit if in truth there really is a correlation. And that would be, so for example, say I had a questionnaire, maybe I had a scale measuring depression, and I had some items on it like I rate the extent to which you feel sad and blue, and I feel hopeless about the future, and maybe I had a reverse scored item saying, when I think about the future, I feel spiffy. That's kind of an unusual word, spiffy. I had a question maybe about when I think about the future, I feel spiffy. And then maybe I had another question that was like, when I wake up in the morning, I feel spiffy. So in this case, maybe I had two questions that both used that word spiffy, which is kind of an unusual word. And maybe people reacted to that word in a similar way so that those two items correlated with each other, even after controlling for the fact that maybe both those items were indicators of depression. After extracting the depression component out of both those items, maybe there was still a spiffy component, that part of how people reacted to the word spiffy. And so maybe those two items correlated with each other even after depression was extracted out. And that's really not something we want. We don't want our items sharing relationships with each other after the factor has been extracted out of them. We want them to be pure indicators of our factors and error variance and nothing else. So that would be somewhat of a problem if you have correlations between your residuals. And so if there actually are correlations between your residuals and you specify that there aren't any, which is what you should do in running a confirmatory factor analysis, then that could produce a poor fit. So here again, a couple of reasons. So we could have, if your items need to load on multiple factors, or you have items in the wrong factors, that could produce a bad fit. Or if your error variances want to correlate, that will produce a poor fit. Now, another thing that actually would cause your error variances to want to correlate is that if your model simply doesn't have enough factors. So actually, these last two things are kind of related because if, so for example, maybe I was wanting to measure depression, and I had some items that were having to, like with thoughts about, I'm hopeless about the future, and I think everything in the world is bad, and I think I'm a failure in life, or some things like that that might all be about negative types of thinking. And maybe I had some other items that had more to do with maybe eating, like recently I haven't been eating very well, or I've lost my appetite. Maybe I have some different items pertaining to eating. And maybe it turned out that the items regarding eating and the items regarding thoughts actually should have been two different factors. And in this case, I'd actually have a problem that the errors that I probably have, the residuals for the eating items might want to correlate with each other, because they have some special communality. They're sharing something special with each other that's not fully accounted for by the depression. They have an eating component that's not fully accounted for by the depression component. And so in that case, my eating items might want to correlate with each other, and it might be a situation where I could fix that by having maybe another factor. Maybe I need one factor for depressing thoughts and another factor for eating items. So if I have a model where I've specified one factor and I really need two, or I've specified two factors and I really need 3 or 4 or 5, or I've specified 4 factors and I really need 5 or 6, if I don't have enough factors, then that could produce a poor fit. Note that this doesn't tell me, we're going to look at this in just a moment, going the other direction, but the fit does not tell me about a situation where I have too many factors. Because if I have, say I had 5 factors, but I only needed 3, well, when I add more factors, I'm making things easier to constrain. When I have if I say I have just one factor, I put more constraints on my model. If I say I have 2 factor, then I'm relaxing some constraints. If I have 3 factors, I'm relaxing constraints. If I had as many factors as I have items on my questionnaire, then my model would be saturated and I'm not making any constraints. So the fewer the factors, the more you're placing constraints on your model. And fit tells you about the reasonableness of your constraints. So it can tell you, a bad fit can tell you you don't have enough factors, but it cannot tell you if you have too many factors. That's a different question. It's an important question, but we'll have to address that one with a different technique, not fit. So fit will tell you if your model does not have enough factors, but it won't tell you if you have too many. We'll have to do something else, and we'll get to that in just a moment, what we do to determine if we might have too many factors. So again, the key thing that we learn with fit is about the reasonableness of our constraints, such as our constraints about which items load on which factors, constraints about how our error variances aren't supposed to correlate with each other, and constraints about the fact that if we have 2 factors, we're having only 2 factors and not more. Or if we have a single unidimensional factor, we have only 1 factor and not more. Or if we have 4 factors, we have only 4 factors and not more. In other words, constraints regarding the number of factors, saying that the number of factors that we have, according to our model, should be enough and that we don't need more than what we have. And the next thing to consider in evaluating a confirmatory factor analysis model has to do with the parameter estimates. Like I've been saying, it would be a bad thing to take a confirmatory factor analysis model and look at model fit and then just stop there. There's more to evaluating a model than simply looking at model fit. Model fit is important, but there are other criteria that are important to consider. And one of those criteria pertains to the parameter estimates. So anytime you do any kind of structural equation modeling, you're going to get estimates for every free parameter in your model. When you specify your model and you designate which parameters are free and which ones are fixed, the ones you designate as free are all the parameters you're telling the computer, estimate these, give me values for these parameters. These are the parameters that are free to be something. So every free parameter in your model is going to get an estimate. You'll get a value for it and you get an estimate for what that parameter is. And you will also get a significance test. So for each parameter, we can look at and find out what is that parameter estimate, what is the value for our parameter, and is that significant? Is it significantly different from 0 or not? So we'll get the parameter and the significance test. So what are the key parameters that we're looking at when we do a confirmatory factor analysis? So we have our item loadings, that's one parameter, all those lambda loadings, the extent to which each item loads on its assigned factor. So we'll have a loading for every item on our on our instrument. And we'll also have, if we have more than two factors and we allowed correlations between them, we'll get correlations between factors. So we have item loadings, correlations between factors. Those are the two key types of parameters that we're looking at when we do confirmatory factor analysis. And for the item loadings and for the correlations, we'll get a parameter estimate and a significance test. And then we can use that to evaluate our model. And the key thing I want to focus on here is the item loadings. How do we look at the item loadings and decide if they're strong enough to support our model? Because if we get item loadings that are weak, that are too small, then that would be a problem. And if I had a questionnaire or assessment instrument and I did a confirmatory factor analysis and had some items with weak loadings, I should not conclude that that questionnaire has good factor validity. To conclude that my questionnaire or my instrument is working well, to conclude that my factor structure is supported, I need to show that I have strong item loadings. So what do I call a strong loading? Again, this is somewhat subjective, as a lot of things we've been looking at through this unit. I can suggest some arbitrary cutoffs. These cutoffs are arbitrary, but there is some support for them. So what I'm going to suggest is that we will call loading of 0.55 or greater good, and 0.45 or greater, we'll call that a fair loading. Now note, actually I'm assuming that these loadings are standardized. That is, I'm assuming that we've turned everything into z-scores prior to analysis, and that I'm looking at these standardized item loadings. If I was looking at a non-standardized solution, then this wouldn't be very meaningful. And usually when you do confirmatory factor analysis, just about any software package you use, and this would be true if you're using the Lavon package with the R program, that when you get output, a lot of times that output will give you one column of unstandardized loadings and another column of standardized loadings. And what we want to look at here are the standardized loadings, the loadings we would get if we turned everything to z-scores prior to analysis. So we'll call a loading of 0.45 or greater, we'll call that a fair loading. That's kind of okay, not ideal, but it's kind of okay. And we'll call a loading of 0.55 or greater, that's what we really want, we'll call that a good loading. And if it's less than 0.45, well, I'm going to say, again, this is somewhat arbitrary, but we'll call that a problem. So if you want to be able to say this scale or this instrument has good factor validity, if you want to say I have support for my factor model, my hypothesized factor model, then we want to have good loadings, and at bare minimum, it should be each item should load at least 0.45 or higher on its scale. That's at least high enough to call it a fair loading. Ideally, we'd want it 0.55 or greater to be a good loading on that item. Now, sometimes I mentioned that we'll get, when we get our results, we'll get values for what those parameters are. We'll get values for what each loading is. Then there will also be a significance test. So we can actually test and see if each loading is significantly different from zero. Now, if you did a significance test and got a non-significant loading, that would be really bad. It's actually fairly rare to have an item that is actually non-significant, because we're dealing with fairly strong effects here. And usually when you're doing confirmatory factor analysis, the loadings are kind of big, and your sample sizes should also be big, and put that together, it's very rare to get a non-significant loading. So, but if you ever do get results and one of your loadings is actually non-significant, then I'd say, well, that's a really bad item. That's worse than worse. That's a terrible item. So loading should be at least significant, but more importantly, we want to look at the size of the loading, and ideally getting loadings 0.55 or greater. One thing to note is that we've talked about identification and how we need to scale our factors, and one of the ways we can do that is by fixing one item on each scale to have a unit loading on its factor. We constrain one of those factor loadings to be exactly 1. At least that's one way. We could also simply constrain the factor to have a variance of 1, but one of the ways we can do that is to fix the loading to be 1. And if we do that, the standardized loadings that we get will be not affected by that. We can still look. It doesn't matter which item we fix to be 1. If we constrain an item to have a perfect loading on a factor, whichever one we constrain, it doesn't matter, we can still interpret the standardized solution, and the standardized solution will not change if I picked a different item and constrained it to be 1. I'd still get the exact same standardized solution. Because in the standardized solution, it won't be 1, it'll be whatever the standardized value is. So the unstandardized solution is what we're constraining to be 1, and the standardized solution will give us the same exact standardized values regardless of which item we constrain to have a perfect loading on its factor. So just noting that won't make a difference for the standardized loadings. However, it will make a difference for one little thing that usually doesn't matter, but whichever item I pick as my scaling item, and if I constrain it to have a unit loading on my factor, whichever item that is, we cannot do a significance test for that item. So I can get the standardized loading, that is the loading if everything was turned to z-scores, and that doesn't matter which one was constrained to be the scaling item. Like I said, those results come out the same regardless of which item I pick as my scaling item. The standardized solution is the same in any case. But whatever item I pick to be my scaling item, that item, we cannot do a significance test for that item. So I'll get a significance test for all my loadings except for the item that I constrain to be my scaling item. And this only really makes a difference if there's a possibility that it might not be significant. Like I was saying, when we do confirmatory factor analysis, usually all the results are significant for all our loadings, and it's really, really bad if we get an item that doesn't have a significant loading. But if there's any risk of an item having a non-significant loading, then we should not use that one as our scaling item. We should pick a different one, because if we do any item we use to be our scaling item, we cannot do a significance test with that item. And the other parameter estimate that we get when we do a confirmatory factor analysis is the correlation between factors. That is, if I have 2 or more factors, I can get the correlation between my factors. And this is a situation where I don't want that correlation to be very high, because a high correlation would indicate that I have problems with discriminant validity. If I have 2 factors and they have a really high correlation, it means there's not much difference between them. Or if the correlation is getting close to 1, it means those 2 factors might be measuring the exact same construct. So to have evidence that my 2 factors are measuring different things, I want to show that the correlation between them is not excessively high. Now, it doesn't have to be 0. So a 0 correlation would be an orthogonal relationship. And we don't have to have an orthogonal solution for our factors to be distinct. They can still have some correlation. We just don't want it to be extreme. Note that when we're looking at correlations between factors, those correlations are actually going to be a little bit larger than the correlations we would get if I just took scores on 2 scales and looked at the regular Pearson bivariate correlation between 2 scales. Because when we do a confirmatory factor analysis, those factors are extracted out of the items, and they're essentially a factor is an estimate of a score without measurement error. And the correlation between factors, when we do confirmatory factor analysis, that correlation is an estimate of the correlation we would get if there was no measurement error. And that's going to be a little bit larger than the actual correlation we would get if we were to simply do a regular Pearson bivariate correlation between 2 variables. So when we look at that correlation between 2 factors, how high is too high? Here are a couple ways we can consider that. One is just to use, once again, some arbitrary, rather subjective cutoffs here. And I have some values. I would suggest that if your correlation between factors is 0.85 or higher, that's a really high correlation. That is, I'd call that extremely problematic. And if you do get that, I have a citation over here from Brown, who suggests that that is indeed a bad, that's a problem, that you should have factors that correlate less than 0.85. And I'm going to go on, and this is just simply from my own experience, I don't have any citations to give you for this, but just based on my own experience looking at results from confirmatory factor analysis models, I would say that even 0.7 is problem. I'd say that's poor. That's a little too high, and I like it to be less than 0.6. So I'd say 0.6. I'm going to give that the label. This is my own personal label. I'll give 0.6 the label worrisome. 0.7 I'm going to call poor, and 0.85 I'm going to call extremely problematic, to give you some general guidelines for evaluating how high of a correlation is too high. So another way we could do this is to say, to evaluate whether our correlation between factors is too high, and this gives us more of a concrete cutoff we could use. We could say that the correlation between factors should not exceed something I'm going to call the square root of the average variance extracted for either factor. So the correlation between factors should not exceed this thing we call the square root of average variance extracted for either factor. So what exactly do I mean by that? Well, let's take a look. So what I'm going to do is I'm going to calculate this thing called the average variance extracted, and then take the square root of it, and I'm going to do it for each factor. So if I have a model with two factors, I'm going to take the items for factor 1 and calculate this thing called the average variance extracted for the items on factor 1, and then take the square root of that. And then I'll take my second factor, the items for factor 2, and I'll calculate the square root of the average variance extracted for the items on factor 2. And then my basic rule here is that I want to look at the correlation between my two factors, this correlation between factor 1 and factor 2, and that correlation should not be greater than the square root of the average variance for factor 1. It should not be greater than the square root of the average variance extracted for factor 1. And it should not be greater than the square root of the average variance extracted for factor 2. So what exactly is this average variance extracted thing I'm talking about? So what I'm going to do is I'm going to take my lambdas here, and I'm going to square each one, and then add them up. So add up my squared lambdas, and then I'm going to take my errors and just add them up. Recall that the errors are variances. These are error variances. These are the residuals that are left over after the factor is extracted out, and they're variances, so they're already squared. Whereas the lambdas are not squared values, so if we want to understand percent of variance explained, we need to square our lambdas. I talked about a while ago the fact that we could talk about that the total variance for an item is going to be equal to lambda squared plus your error variance. We squared lambda. We don't need to square the error because it's already squared. So lambda squared is a percent of variance explained. Error is simply the percent of variance not explained, and lambda squared plus error is the total variance. So if we sum up all of our squared lambdas plus all of our errors and add that all together, that is actually the total variance. And I'm going to put that right down here in my formula here. The sum of my errors plus the sum of the lambda squares, that is the total variance. And then I'm going to take the sum of the lambdas, that's the explained variance, and put that in the numerator. So I've got an equation that's saying the explained variance, the sum of the lambda squares, divided by the total variance, and that's going to give me the percent of squared variance explained. And then I want to turn that into an unsquared format, so I'm going to take the square root of that. So I take the square root of this percent of variance explained, and that is the square root of the average variance extracted. Or I suppose it's using the language variance extracted rather than variance explained. It's kind of two ways of saying the same thing. The technical term here is the average variance extracted. So the square root of the average variance extracted. And so once I calculate this square root of average variance extracted, I simply compare it to this correlation between my two factors. And I'll calculate an average variance extracted for the items on factor 1. I'll calculate it for the items on factor 2. And this correlation should not be larger than either of those average variance extracted values. And this slide is simply listing a few things to keep in mind when you calculate the square root of the average variance extracted. Like I mentioned, the lambdas need to be squared before you sum them, whereas the errors, the residuals, are already squared. They don't need to be squared. Note that you calculate a separate average variance extracted for each factor, and you would only sum the squared lambdas and the errors for a single factor at a time. So if you have a model with 2 factors, you would sum all the squared lambdas and errors for factor 1 and get an average variance extracted for factor 1, then take the square root of that. And then you would do it all for factor 2, and you get one average variance extracted, or a square root of average variance extracted for factor 1, and you get a separate square root of average variance extracted for factor 2. And another thing, if you wanted to, the reason why I have you taking the square root of the average variance extracted is because we're comparing it to a correlation, and a correlation is not using a squared metric. If you wanted to, you could square your correlation, and if you want to take r squared, then you can compare that with the unsquared, just the average variance extracted. So to make these two comparable, we either need to take the square root of the average variance extracted and compare that just to the plain simple correlation to r, or you could not take the square root of average variance extracted and instead compare that to your r squared. Either way it will work. My thought is it seems simpler just to calculate this square root of average variance extracted and then just compare that with your regular correlation. But if you wanted to, you could not take the square root of your average variance extracted and instead just simply compare it with your r squared is another way that would produce the exact same result. Finally, the third thing we want to look at when we're evaluating a confirmatory factor analysis model is that we want to consider alternate models. And this is actually something that is true when you do any kind of structural equation modeling, that if you test a model and you get a fit, so we get the fit of a confirmatory factor analysis model, and even if that fit is really good, we get a model that has a really good fit to it, that never rules out the possibility that another alternate model might fit equally well or possibly even better than the one we tested. So just because we get a good fit, that doesn't mean it's the best model. There might be other models that fit equally well or almost as well or even better that are important to consider. And when we do a confirmatory factor analysis, the key question here is whether there is a model with fewer factors that might fit. So if I have a model that, say I have a questionnaire and it's supposed to measure, maybe it has 3 scales, and so my model is that there are 3 factors, but would a 2-factor model or even a unidimensional 1-factor model, would a model with fewer factors fit just fine? Do I really need all 3 scales? Do I really need 3 factors? Or would a model with fewer factors fit just fine? Note that when we talked about the fit, that if we have a model that has a poor fit, that could be caused in a situation where we don't have enough factors, but having too many factors will not reduce our fit. So not having enough factors will cause a bad fit. Having too many factors will not cause a bad fit. Having too many factors will not reduce your fit. And that's because when we add factors, that always makes our fit better. Because when we add factors, we're reducing the constraints on our model. When I remove factors, when I look at models with fewer factors, that's adding constraints. So in other words, if I say I have a set of 10 items and I can explain the variance in these 10 items with just 1 factor, that's more constrained than if I say I can explain the variance in these 10 items with 5 factors. If I'm trying to explain variance with 5 factors, that's a looser model that has fewer constraints. It's more relaxed. If I say I'm going to explain all the variance in those 10 items with just 1 factor, that's a more constrained model. So when we remove factors, we're adding constraints. And if we add factors, we're reducing constraints. And therefore, models with more factors will always fit better than models with fewer factors. And so we can't tell if we have too many factors by looking at the fit. We could have an excellent fitting model that maybe has 3 factors, but the question is, well, how would a two-factor model or a unidimensional one-factor model do? Would that fit almost just as well? Now, it's not going to fit better if we go from a two-dimensional model to a one-dimensional model. That can't possibly make the fit better because we're adding a constraint. But if we go from 2 dimensions to 1, the key question is, would it make that much difference? Could I still get a reasonably good fit with a one-dimensional model, even though my theory is that I should have 2? So we want to look at ways that we can address this question. Again, we can address the question of do we have too many factors is the one we're looking at here. The question of do we need more factors, that's with fit. So a bad fit can tell us we need more factors. It can't tell us we have too many factors. To determine if we have too many factors, we need to compare our model with another model that has fewer factors. So that's what we're going to look at now. So say, for example, let's say I had a 10-item questionnaire that was supposed to measure anxiety and depression. Maybe I had these 2 factors. Maybe there were 5 items that were supposed to be measures of depression and another 5 items that were supposed to be measures of anxiety. So my hypothesis was that this instrument should be comprised of 2 factors. And let's say I did a confirmatory factor analysis and my model produced a good fit. And like I've been saying, just because that model produced a good fit doesn't mean that other alternate models might not fit nearly as well. And the key question here is if my hypothesized model has 2 factors and it fit well, what would happen if I tested a unidimensional one-factor model? Would one-factor model fit just about as well? Now, of course, if I go from 2 factors to 1 factor, it's not going to make the fit better. It can't possibly make the fit better because when I go from 2 to 1 factor, I'm adding constraints to my model, and that will always cause a reduction in the fit to some degree. But the big question here is, will it be a trivial reduction, or will it be a substantial reduction? Or will it be a reduction that's not so bad and my alternate model still fits pretty well? Here I have 3 possible ways we could go about evaluating this alternate model. And if it passes one of these, whichever criterion we're using, and we say, well, this model actually is, if the alternate model is actually working well, then that would be a problem for the factor validity of our questionnaire. We don't want this alternate model to fit well. What we're looking for is a situation where our hypothesized model works really well and the alternate model is terrible. So that we can say our hypothesized model is the correct one and the alternate model doesn't work. If I got results that showed this alternate model was actually working pretty well, then I should probably reject my hypothesized model because the alternate model is more parsimonious. If my hypothesized model had 2 factors and the alternate model only had 1, then the alternate model is more parsimonious. It's simpler. It doesn't have as many factors. I'm explaining my items with fewer things. And that's always a better approach to take if I can take it. So if my alternate model works well, then I would need to reject my hypothesized model and say this alternate model is better because it's more parsimonious. So if I want to support my hypothesized model, what I need are results that show this alternate model is bad. It's not working well. And here are 3 different ways that we could test our alternate model to see how it's doing. And the first is really simple. We just look at the fit of the alternate model. And if the alternate model has a poor fit, we say, well, that's bad. We reject it and say, yep, that's working. That's what we were hoping for. Our hypothesized model is the one to go with. This alternate model produced a poor fit, so we're going to reject it and dump it down the drain. So we could simply look at the fit of our alternate model. A poor fit means we reject it. Or if that alternate model fits well, then we say, oops, that's not what we wanted, but look at that. The alternate model is fitting well, so I guess maybe we should use that one, even though it wasn't what we were expecting. Another thing we could do is, now recall that I mentioned that when we go from 2 factors to 1 factor, or if we're going to reduce the number of factors in our model, that's essentially adding constraints. And when we add constraints, it's always going to reduce the fit to some degree. And so what we could do is say, well, exactly how much does it reduce the fit? Does it reduce the fit by a trivial amount or a great big amount, which means we need to find some kind of way to define what is a trivial amount. And one rule of thumb I have here, which there actually is a paper that would support this, or someone else has suggested this, is to look at that comparative fit index and look at the change. So if you get the comparative fit index for your hypothesized model and get the comparative fit index for the alternate model and look at the difference between the two, and if the change is greater than 0.01, you would call that a meaningful magnitude of difference, and therefore say that you should reject the alternate model, that the alternate model made things worse by a meaningful amount, and therefore you're going to reject it. So one way to do it is say if the comparative fit index, if the difference between the two models is greater than 0.01, you will call that a meaningful magnitude of change, or a meaningful reduction in fit. And therefore you could say that this alternate model is a meaningfully amount worse than your hypothesized model, and that would provide support for your hypothesized model and be a grounds for rejecting the alternate model, because it made things meaningfully worse when you added the constraint of reducing it down to, say, just one factor. So if the comparative fit index is greater than 0.01, that's called a meaningful magnitude of reduction in fit, and that would be evidence against your alternate model and in support of your hypothesized model. That is, assuming your hypothesized model was significant to begin with. If your hypothesized model didn't have a good fit to begin with, then all of this is moot, because you wouldn't accept them if it didn't have a good fit to begin with. Then it's not the right model. So then the third thing is that we could test a significance. So number 2 here is looking at the size of difference in fit between your alternate model and your hypothesized model. The third thing we could do is to test for significance, to see if there's a significant difference between those two models. So we're going to say, is there a significant reduction in fit? So if you look at the fit of your hypothesized model, the fit of the alternate model, and as I've been saying, your alternate model is going to have a poorer fit. That is, if you're going from, say, more factors to fewer factors, the alternate model will always have a poorer fit. But we could say, is that reduction in fit significant? So number 2 was looking at the size of that reduction in fit and saying, was that a meaningful magnitude of reduction? Number 3 is looking at the difference in fit between the two models and asking, is that difference significant? And so we could do a significance test and get a p-value to see if there's a significant difference between the two models. And if you're wanting to test for a significant change in fit between two models, that is often a fairly easy thing to do with structural equation modeling. So if I have two models, and I'm going to call one model my target model, and this will be my hypothesized model, the one I'm hoping to support, and so I'll call that my target model, or model T. And if I alter that model by adding constraints, and if I go from, say, a two-dimensional model to a one-dimensional model, that actually is produced by adding constraints to my model. As I talked about a moment ago, when we reduce the dimensions or we reduce the number of factors in our model, we're essentially adding constraints. And so if I have a target model and I create this alternate model by adding constraints, and I'm going to call that alternate model model C. So I have my target model and this alternate model model C, and if the difference between the two is simply that I added constraints. So I had my target model T, and I created my alternate model simply by adding constraints to that target model. In this case, these two models are nested. So nested models is a situation where I start off with a target model, and I create an alternate model simply by adding constraints to my target model, and then I have what we would call two nested models. Model T is my originally hypothesized model, and model C is the one that I created by adding constraints, and they would be nested. And when I have two nested models, there's a very simple chi-square test you can do to test for a significant difference between those two models. So and this would be, now it's really easy if you have items that are continuous and you've used maximum likelihood as your estimator. And let's start with that because that's a really easy thing to do. We can calculate this thing called a chi-square change, or have that delta symbol for change, or change chi-square. So I'll calculate this value called a change chi-square, and I simply get the chi-square value. Recall that when we run our models, we get our fit output, and one of the statistics that we look at in terms of fit is our chi-square. So I'll get the chi-square for model C. I call that maybe my constrained model. And I get the chi-square value for model T, that is my originally hypothesized model, or my full model. And I'll take the chi-square for model C minus the chi-square for model T, and that simple difference, that simple subtraction, will give me the chi-square change. And to determine significance of chi-square, this is just basic significance testing, you need to know the chi-square value and its degrees of freedom. So if you know the chi-square value, degrees of freedom, then you can determine the probability of that chi-square if the null hypothesis is true by looking it up on any, you could look at say, a chi-square table in the back of any statistics textbook, or you could go online and look at a chi-square calculator or use a computer. So it's just the basic process of once you have a chi-square value, if you know the degrees of freedom, you can determine the probability of that chi-square value. You just look it up on a table or use a calculator or go online and get the probability of that. And the degrees of freedom for your chi-square change is simply degrees of freedom for your constrained model minus degrees of freedom for your full model, or model T, and that will give you the change degrees of freedom. So simple subtraction, you can get a change chi-square and get a change degrees of freedom, and then you just use any chi-square table to look that up to determine what the probability value is for that. And if your probability is less than 0.05, then you say it's significant and you have a significant difference between your two models. And in this case, if you were comparing, if your model T was your hypothesized model with, say, 2 factors, and the constrained model was the model with just 1 factor, and you did this chi-square significance test and you got a significant difference, that would be cause for rejecting the constrained model. That would be what you'd be hoping to find. You'd want to find a significant difference to show that your constrained model is significantly worse than your hypothesized model. If this wasn't significant, then that would be a failure to show that your model was any better than the constrained model. That would be a failure. If it's not significant, that would be a failure to demonstrate that your hypothesized model is any better than the alternate model. There was no significant difference, and in that case, you might as well just accept take the alternate model because it would be more parsimonious with fewer factors. Then finally, I note down here at the bottom that that if we're using ordinal items, like what we probably are for evaluating a questionnaire, if I have discrete or ordinal items, say with response options, maybe 5 or 7 levels of response option for each item, that's what we've talked about before. We talked about how we could estimate that with diagonally weighted least squares in that situation. And I mentioned how in that situation we would also use an adjusted chi-square value. And if we have these adjusted chi-square values, that's what we should be using in this chi-square difference test. And sometimes there are other things that make that somewhat complex, although if you're using computer software to do this analysis, it can take care of that for you. But the chi-square difference test gets a little bit more complex, and we need to use these adjusted values in situations where you're using ordinal or questionnaire items that have only a few levels, like 5 or 7 levels to them. If you're using ordinal or discrete items, then we would use these adjusted values, and it makes it a little more complex. But either way, we can still do the significance test and see if there's a significant difference between your hypothesized model and the alternate model with fewer factors. And in this case, we want it to be significant, because if it's significant, that means that the alternate model is significantly worse than your hypothesized model. Therefore, you would support your hypothesized model and reject the alternate one in that situation. And that is everything I have for you for this main unit on confirmatory factor analysis. One additional topic we could consider is measurement invariance, but I will save that for another time.